Let's do this thing.
It is.
What's that? Table's wobbling?
Yeah, that's what I'm
Is that the first time? It's, yeah. They might have switched tables. They kind of do that. Yeah. Okay, so this is that microwave background that's like the hiss from the beginning of the universe. So that's like in microwaves.
That was cool.
That was cool. Okay. And I think I've played this before, but if, let's see, I'll go ahead and play it. But basically, this is going to emphasize the whole, everything used to be, I think that video did a good job of saying how basically the universe used to be what we call actually a singularity, and then it expanded. It's been expanding ever since. And so we've seen something like this before in here. Those are not like mouse pellets. Those actually are galaxies. Okay, so it looks like this. So it's kind of going back in time. Okay, so if we're expanding now, this is actually then contracting. The G actually stands for billions of years. Okay, so going back in time, that's kind of the fabric of space and time. Also got smaller. Okay, so not only were we smaller, the universe was smaller, but you probably picked up from the video it was a lot hotter. Okay, and so I have a few slides that talk about how hot it was. So what this slide is, along the y-axis is temperature, and along the x-axis is time. And so the way the time is set up here is actually, this is in seconds, and we're using scientific notation here, so 10 to the negative fifth. And so this is actually 10 to the 0th, or 1, okay? So this is 1 second after the Big Bang, okay? And so you can see what the temperature cooled down to 1 second after the Big Bang, okay? So it was way hot before. And to kind of emphasize how hot it was, 10 to the 32nd, that's in units, the temperature is in Kelvin. So it's that many units in Kelvin, okay? That's how hot it was early on, okay? And so it expanded, and as generally as things expand, they cool down. So in case you're wondering if this is 1 second after the Big Bang, I know it sounds kind of strange, but actually 4 times 10 to the 17th seconds is where we're at in time approximately after the Big Bang. You're like, really? But that means like, 17 zeros after the 4 in seconds. So that's kind of fun, actually. So if you look at it that way, then, this actually should be our current temperature in units of Kelvin. That's how that works. And so actually, the temperature of the universe is running about 3 Kelvin, the temperature of the universe. The temperature of the Earth is about 298 or 300 Kelvin. And the fact that the temperature of the universe in our vicinity, anyway, is about 3 Kelvin actually supports what we understand about kind of the different stages of the Big Bang. But here in a minute, we're going to talk about, there's a whole bunch of stuff that happened here. Are there 9 eras, did we say on the review sheet? Okay, 8 eras. The 8 eras of our universe, they hope happened in here-ish, okay? So, like, just a fraction of a second. So I think that they did a good job on, did you catch the beginning of the video about the matter and antimatter? And the other thing is, he wrote it in white chalk, he wrote E is equal to mc squared. So basically the universe started out with a lot of energy, okay, and you can go back and forth between energy and matter, okay? Einstein says you can. But the first matter to be created was a pair of particles that were, let's see, how do I say this? There was matter and antimatter, just like Star Trek. And when they come into contact, they annihilate each other, okay? Which is problematic. So if we kind of look at the eras, not broken down, but we have the initial Big Bang, okay, and we'll talk about what's so special about a time of 380,000 years after the Big Bang. You're going to see that number again. Okay, and this is just kind of showing the expanding universe. Okay, so those 8 eras that the video didn't talk about, I'm going to kind of briefly talk about. But the 8 eras can be defined with regard to temperature and a little bit time. Okay, the eras can be defined as to what particles are there in the universe during that era, or created during that era. The other thing, these 8 eras are described as terms of these 4 forces. Okay. So the 4 forces are gravity, electromagnetism, which I had a hard time spelling on the review. Okay. And then we have the other 2 forces, weak force and strong force. And I'm not going to necessarily emphasize it, I think, tonight. But these things might be kind of strange to you, but if you look into them, actually, they have to do with the atom. And since all things are made up of atoms, they are actually very important. But we're probably familiar with gravity and, to a certain extent, electricity and magnetism. Okay. But on your test, be able to name these 4 forces. So here's the thing about these 4 forces. Right now, we definitely have, we not know the inner workings of it, but if you have atoms, you have the strong and the weak force, okay? We have gravity, we have this other force. That's what we have right now. We didn't always have these 4 forces separate. So what this is going to show you is those 4 forces, okay? Kind of starting now, it's going backwards. So over here-ish, let's see, is this right? Over here actually is the present time. And just fractions of a second going closer to the present time. So the Big Bang is over there. Big Bang over there, present time here. Okay. And then along the x-axis down here, we have temperature. So we have the cooling off, okay, expanded and cooled, hot, getting cooler. Okay, so here are the 4 forces. So I said the 4 forces: gravity, electromagnetism, and then you see that strong and the weak force. So their 4 are separated right now over here. Okay, cooler universe, definitely have 4. That wasn't always the case. Going back in time, okay, actually if we pick on the electromagnetism and the weak force, okay, they used to be a force together called the electroweak force. And then if we throw in the strong force, and I think this might be on your review sheet, I'm not sure. Do I have gut force? Okay. So going back in time, actually, the strong force then joined in with the weak and electromagnetism force. Notice we have the outlier force, the problem child down here, gravity. Okay. So, and actually we're going to see the gut force kind of breaking out into the strong and the electroweak force. That defines one of the 8 eras. But notice, keep an eye on what time we're talking. We're talking a fraction of a second, okay, after the Big Bang. Oh my gosh. Okay. So as far as going back to the Big Bang, did the 4 forces unite? Again, 2 forces are united when you talk about the electroweak force. 3 forces are united when we talk about the gut force. Okay? And so then going clear back to the beginning of the universe, was gravity maybe there in with the other 3 forces? Possibly. So string theory, I think, has been around. It's a branch of physics. And I think it's been around for maybe pushing 20 years. There's a video out there, a documentary called The Elegant Universe, and it's a beautiful documentary. And a lot of it is based upon this cool aspect of string theory, which basically breaks down, it kind of does what our particle accelerators are doing. String theory breaks down your protons and your neutrons and your electrons into these cool vibrating strings. Okay? So, yeah.
So just to clarify, where it says superforce, that was like the Big Bang, and so then
Right, exactly. Superforce would be with the Big Bang, and superforce would say, hey, maybe gravity was there with the other 3 forces. And I think when they talk about a unifying theory, I think that's what they're talking about, I think. Yeah, because the elegant universe talks about the unifying theory. Okay, so here comes your 8, count them 8. And what I told my other class is with these 8 eras, kind of see something that you'd like to explain to your dog or something. Okay, about the Planck era, you could say it was the first era. Okay, it was the first and it was the hottest. So just to kind of emphasize when it says 10 to the negative 43rd seconds, down here at the bottom on these slides, I went ahead and showed you what that means. It's that fraction of a second, okay?
This was
The first
the
of 8.
first fraction of a second after the Big Bang.
Mm-hmm.
Okay.
Yep. Okay. And it says all forces may have been unified. This middle column on these figures, actually, this middle column kind of shows you what was the particulates like. Question mark, really don't know what sort of matter we might have had then. You might imagine the farther you go, closer you go to the Big Bang, the more it's like uncertain. So after the Planck era came the Gut era, and do you recognize Gut was one of where we had 3 forces that were unified. Okay, so in the Gut era, at least you had gravity was clearly distinct from the other 3 forces. I don't have a whole lot to say. And then the Gut era ended when the strong force broke away from the weak and the electromagnetic force. One thing about the Gut era you could note is here in a little bit we're going to talk about this thing called inflation. Inflation isn't an era. Inflation is a phenomenon. Okay, and if you think of inflating a balloon, that's what inflation is. Okay, and so that important thing happened at the end of the Gut era. Looks like. Still no particles. Not my favorite. Okay, electroweak era. Okay. Electroweak era. See, you see these. You have some little particles showing up. Okay, elementary particles.
So then the strong force is by itself, and the weak and electromagnetic are together still.
It looks like at the end of this. Yeah. But I think at the end of this one, that's what it says. Yeah. At the end of this one, it must be the electromagnetic and the weak broke apart. Yep. There's the fraction of a second. My favorite ones are coming up. All the while, though, and I hope you kind of got this, I haven't emphasized it, but are you picking up all the while through these eras? Fraction of a second, the universe is cooling. And it's important that the universe is cooling because at some point we finally get things when they don't have as much motion to go ahead and grab hold of each other. Okay, so the particle era then is where don't quite have not molecules. We don't quite have atoms, okay, but we're getting closer to having atoms. So the particle era, I guess maybe you can think of the energy is equal to mc squared, where basically energy, it's cooling down, we're getting more and more energy converted to matter. But the problem is, like I said, during that process, usually you get matter and antimatter in equal amounts. And this slide kind of emphasizes that usually you get them equal amounts, but for every 10 to the 9th pairs that are going to annihilate each other, one of them is regular matter. Doesn't have antimatter that's going to annihilate it. So it's kind of a slow process to create matter. So that's a particle era. It keeps cooling down. And then you might see the word nucleus kind of in nucleosynthesis. And nucleus there, we're talking about the nucleus of an atom. So era of nucleosynthesis is not quite have a bunch of little atomic nuclei, but we're getting close. We're starting to make.
5?
Is it 5?
Yeah.
Okay. So we're getting closer. Nuclei are beginning to fuse. And I don't know, this to me seems similar to nucleosynthesis, the era of nuclei. You have arrived. It's cool enough to go ahead and get a healthy amount of nuclei. That's the center of atoms. And when you think of atoms, you're probably kind of, the simplest atom is hydrogen, then we have helium is the next simple atom. And after that is the element lithium. Okay, so that's cool. Then after we get nuclei, then we can go ahead and have atoms. So the difference between the nucleus of an atom and a regular atom is electrons. And this actually, the video did address this. Okay, basically, remember when they said that it went from being foggy to being clear? That's this time. And remember I said a little bit ago on that figure there was the 380,000 years after the Big Bang? Okay, that's this time. The time when basically nuclei and electrons find each other. It's cool enough. Okay, then we have atoms, era of atoms. And the thing about it stopping to be foggy is basically those electrons, those pesky electrons, stop messing with your energy that wants to escape, your light. So they settle down and things can kind of become clear. And so when Penzias and Wilson were looking at they cleared their pigeon droppings from their radio telescope, and they were looking at the Big Bang, okay, that energy could only be released from the edge of the universe when it settled down into form atoms. So, okay, so this is the last era, and this is the era we live in. So,
Sorry.
you're fine. It's actually cooled down enough to go ahead and there's a big step going from atoms to galaxies of stars. We know that. And I liked the video because it kind of talked about that. All right. The History of the Universe, that actually is the title of the video, National Geographic video we watched. Okay. So those 8 eras, okay, kind of generally kind of walk you through our universe expanding and cooling down and kind of the major steps of things that happen. And actually, that kind of series of events is supported by 2 main things. One of them is the Penzias and Wilson thing, the hiss from the Big Bang. And the other is just generally when we look at our universe, how much hydrogen and helium do we have? Those 2 things kind of support, what we know about the Big Bang. So these are the guys we saw actually, don't know which one we saw interviewed. Might have been this guy here with the tan pants. But you see them standing in front of their radio telescope. Very exciting. And I'm pretty sure that they earned a Nobel Prize for that. So this, I don't know if this is in your notes, but I was just going to kind of emphasize again, when they looked for the hiss, okay, to create the cosmic microwave background, the CMB, they actually are looking at these long energy signals, okay? That one. So this slide is kind of emphasizing that the era of a nuclei versus the era of atoms. Okay, era of nuclei, era of atoms. The difference is those pesky electrons have found homes, and they're not going to block that energy from us being able to see it. And you see the corresponding temperature of the universe runs about 3,000 Kelvin at that time. So earlier in the course, we talked about kind of an energy signature kind of being corresponding to a particular temperature. I'm drawing a blank, but that's what this is. So actually this particular signature of energy coming from basically our horizon of our universe, our cosmological horizon, actually corresponds to a temperature of almost 3 Kelvin, 2.73 Kelvin. So the deal is, instead of, it's about 3 Kelvin instead of 3,000 Kelvin because of redshift. And we talked about assortment of different redshifts, but we talked about one that's called the cosmological redshift, where basically the fabric of space and time are elongating. Okay, that is actually what is creating this longer wavelength. Okay, so the lower temperature, even though it's really 3,000 Kelvin, it comes to 3 Kelvin. So this is we saw this figure, kind of, again, it's showing you the, I could show you, but it shows you the little speckles that actually are the signature from our cosmological horizon of the Big Bang. I liked the video because I couldn't remember what it was, but your FM dial, if you kind of find stations between your FM dial, that's like a percentage of that is what they got. So I don't know if you caught it, but that kind of gold-looking spacecraft, okay, that was actually a NASA mission that's been up there collecting data in that microwaves to create these maps called WMAP. Okay. So what we know about the Big Bang is supported from that cosmic microwave background that Penzias and Wilson saw. It's also supported by, in general, when we look at the universe, how much hydrogen and helium we have. And that's what the next few slides talk about. So I know it seems like when you look around this room, you think, oh, there's hydrogen, you know, because like plant life has hydrogen.
I will search for an answer to write. You have no new messages awaiting a reply.
What the hell?
I've heard of such things. They just go off.
It's talking to me. I don't even know.
That's weird.
I thought it was his phone.
You're like,
anything
rude.
My phone's on silent. Anyway, sorry.
So I bet your phone has got lots of metal in it and such, right?
Yeah.
But in general, if we're trying to understand the Big Bang, and I thought the video did a good job of kind of talking us through, we only have simple stuff to start out with, right? So right now we see about 75-25 hydrogen helium, and that makes sense when you consider how hydrogen turns into helium, kind of in this way. So another way that kind of when we survey the universe, it makes sense, the relative amount or abundances of the elements, is this. It's kind of summarized here. This is kind of a really busy slide. I was looking at it in my office. I'm like, what? Okay, so let me try to kind of clarify a little bit. Basically, we really think that, like this says, at the time of the Big Bang, with regard to ordinary matter, you're looking at about 4%. 4% of the matter early on that was created from our Big Bang was 4% ordinary matter. So then that actually corresponds to what we see with regard to special hydrogen called deuterium, and what we see with regard to the amounts of helium, and not bad with regard to lithium. So it's a busy slide. Okay. But bottom line, if you're like, I have no idea what that was, just be able to check the two things that support what we know about the Big Bang, that background radiation and the abundance of the lighter elements. So there are definitely still some things not explained so far in what I've told you. And one thing that can one thing that astrophysicists or cosmologists, or the folks that understand the Big Bang, have inserted into the goings-ons is this thing called inflation. And I told you to think of inflation, just think of inflating a balloon. And that's kind of what inflation is. Okay. So this slide is trying to kind of show you inflation. basically in a matter of 0 time, okay, our universe, just like I told you, a balloon, it basically went from this size to this size, okay? So it had normal accelerating expansion, inflation, and then normal accelerating expansion, okay? So the thing about inflation is, what this says is, I know, remember the video we watched, and it talked about kind of those little bumps, the irregularities in the signal, okay? Those irregularities are important because those are, these slides call them seeds. Those are actually seeds for, you can have like little clusters of materials where you can have stars to be formed. So those seeds actually were important. Those seeds are actually these kind of little bumps. Okay, so basically the universe was this size, inflation, okay, like that. So one of the things that Penzias and Wilson saw is like we would be that little black dot right there, okay, and we look anywhere in our sky and we basically see the same radiation signal, the same hiss. And you're like, how could that happen? Okay. And that actually could happen if we insert, these are the two regions, A and B right now, okay? And this is showing you basically inflation right there, okay? And then normal expansion. Okay, so do you see the inflation and then normal expansion? So, might be one of those things to stick under your pillow. But that's how you explain that the sky looks the same like that. Now these next few slides about the shape of the universe, okay, I don't have any test questions over it, because frankly, every time I get to this part, I'm like, well, now what is that? Okay, but if you're a physicist or an astrophysicist, you know that with a certain amount of energy and matter and density of that matter, actually the fabric of your space and time can have an assortment of shapes. Okay, so our shape, to me, what this is saying is what could appear to be flat actually could have started out as curved. Okay, so there's no questions over those. So this actually then is the cosmic microwave background photo again of our universe. And so you can kind of see that if you look close enough, it has these little fluctuations, these little things, these little seeds that can go ahead and create locations of star formation within galaxies. This actually is looking at the previous map, looking where the little clusters of matter are, those little seeds that can form galaxies.
So they're saying that the seeds or whatever came about because of the inflation.
Mm-hmm.
Otherwise there wouldn't be those.
Right. The seeds have been magnified from kind of fluctuations before inflation. Okay, yep. Can't remember what all this says. So I know I'm leaving out, filling in blanks of how they know this, okay? But kind of come full circle a little bit when we said that in the chapter 18, okay, we said that we kind of saw these statistics. In our universe, we have a lot of dark matter and dark energy. And actually that all kind of ties back into the cosmology that I presented with the 8 eras. And the overall geometry of our universe is flat. And throw in the idea that those weakly interactive massive particles, those WIMPs, they just work right along with the physics of of what we see in this cosmology. So the last topic to cover is also, I think I'm going to go ahead and play this little video for you. It's called Ober's paradox. Ober's paradox. And to me, what a paradox is, it probably is to you, don't you think of something kind of like, well, it seems like it should be this way, but it's really this way, sort of kind of a paradox. Let me see if this is the video. I think it is. And it's the same everywhere. It's here, it's there, okay? Basically, do you see, if it's been around for, since ever, forever, then light that, for instance, that was stars that were 20 million, billion, that stars that are 20 billion light years from us, okay, they would have had forever for that light to get to us. Okay, so we'd have that light. Stars that are 30 billion light years from us, we'd have that light, and that's what it's talking about. Basically, our skies would not be dark because we'd have all of that light. Okay. So, if this were the case, basically the skies would not be dark at night. Stars would cover the skies. I'm not sure, I know your textbook uses an analogy of a forest, but I'm just not quite sure how to use it. Okay. But this last slide says, this is the last slide? One more slide. Okay, but it just says that, like, when we look up at the nighttime sky, we do see a dark sky. And so the premise that I said before, the whole fact that the universe is infinite, it's not infinite, it's finite. It had a finite beginning. It's finite and it's changing and it's not everywhere the same. Okay. So that's it, I know. So actually, yeah.
Sorry.
So actually the Ober's paradox would be almost a third thing that supports the theory of the Big Bang. Okay. Well then, if you guys are okay with calling it a night.